with the numerical model. There are also specific objectives that I will deal as the presentation goes on. As a short introduction to the topic, we know that crack propagation can be applied in loading in pure loading mode or mixed mode. In pure modes, we have the opening mode or mode 1. We have mode 2, which is in plane shear, and we have mode 3, which is the tearing mode or out of plane shear. And then we have mixed mode when we have two or more of these modes happening concurrently at the crack tip. For the mixed mode in particular, there are a few tests that we can use to characterize the materials and the adhesive joints. In this case, we have the symmetric double cantilever beam. We have the asymmetric tapered double cantilever beam. We have the cracked lap shear, and the one that we address in this work to assess the effect of the adhesive thickness, which is the single leg bending test. In this work, the geometry that we are going to consider has the layout and dimensions that I show in this slide. So this is basically an ENF test for pure mode 2 testing, but in which the lower adherent is shorter. So at the crack tip, we are going to have a combination of tensile and shear stresses. In terms of materials, the adherents were made of a composite preg with a seal Texipreg 160 RM, which will be addressed in the numerical simulations as elastic orthotropic with these properties that were previously defined in the previous work and which will be directly applied to the models. We are going to consider a polyurethane-based adhesive, the Force 7752, which is considered a structural adhesive and which was already characterized regarding mechanical testing and factor testing in previous work. We can see from the tensile and shear fracture energies that comparing to typical adhesives, this is a highly ductile adhesive. But on the other hand, if we take a look at the tensile strength and shear strength, it is an adhesive that falls short, for example, when compared with epoxy adhesives. Experimentally, we carried out the tests for the different adhesive thicknesses, and here I present a sample of the fracture envelope of the tests for an adhesive thickness of 1 millimeter. In the numerical models, we are going to use a power law function to access mixed mode fracture with an exponent alpha that is going to vary between 0.5 and 2. These are the respective functions. The straight line is the linear power law, and we saw that this adhesive experimentally gives us a fracture law exponent of 2, which is somehow different, for example, to epoxy adhesives, which are typically under a law of 1. But in this case, we calculate and we saw that it was a value of 2 for all of the adhesive thicknesses that we test. Going to the numerical part, we carried out the analysis in the Abacus software. We consider the adherents as elastic orthotropic, as I said before, and we model the adhesive layer by a triangular shape or a bilinear cohesive zone model. We consider the power law that I showed in the previous slide for cracked propagation. We are going to consider an exponent of 2 as exponent of the models because we defined that parameter experimentally. And we can also see some details about the mesh. The mesh is typically more refined at the vicinity of the loading cylinders and also more refined at the region of crack propagation of the SLB specimen. These are the first results in which we compare the data. Here we compare the P delta curves for 0.1 millimeter and 0.2 millimeter. We have made this analysis individually for each specimen, and we can see that comparing the numerical curve with the experimental one, in both cases we have a good representation of the experimental behavior, although experimentally many times we had episodes of abrupt crack propagation, which of course does not occur in the numerical models. Here we have the results for the thickness of 0.5 millimeters and 1 millimeters. The stiffness is once again practically the same. We had a good agreement in the maximum load, although in these two specimens in particular, we had an abrupt failure that occurred experimentally. The biggest difference that we had was for the adhesive thickness of 2 millimeters. In this case, there is a slight variation in the Pmax, in the maximum load, and a higher deviation in the displacement corresponding to the maximum load, which leads us to believe that this triangular law becomes less suitable as we increase the adhesive thickness to higher values. Here we have a summary of all of the results that we obtain divided by adhesive thickness. This is, for example, for an adhesive thickness of 0.1 millimeters, we have the experimental maximum load, the experimental displacement at the maximum load, and we have the equivalent numerical values for all of the 5 specimens that we tested for each adhesive thickness. We have the individual variations, specimen by specimen, and the average deviation in the Pmax and in the delta Pmax. These values of 475 and 677%, they are acceptable, and we can see the same values as we increase the adhesive thickness. These are the values for 0.2 millimeters, the values for 0.5 millimeters. Here we start to have more deviations, specifically in the displacement at the maximum load for 1 millimeter of adhesive thickness. And finally, the worst results that we obtain, as we saw in the curve, are the results for an adhesive thickness of 0.2 millimeters, in which the displacement has a difference of almost 17%. These are the fracture envelopes that we obtained numerically. So in the numerical simulations, we input always the power law of 2, and ideally we should get also the power law of 2 as the result of the data analysis to the numerical data. We obtained that for a thickness of 0.1 millimeters and 0.2 millimeters. The results are agreeing with the input of an exponent of 2. But as we increase the thickness of the adhesive, we started to have slight deviations for 0.5 and 1 millimeter, which the proposed exponent in this case is 1.5. And we had the biggest deviation for an adhesive thickness of 2 millimeters, in which we input a power law of 2, but our results resulted in an output 1. We consider that this may be related to the using of a triangular shaped cohesive law to an adhesive that is extremely ductile and leads to these increasing deviations as we further increase the adhesive thickness. We performed a sensitivity analysis to the parameters of the adhesive law. So we considered our numerical models for typical adhesive thicknesses. Here I just present 2 examples, and we vary the input parameters to see what is the effect on the P delta curves. We can see that varying G1C has a significant effect in the P delta curves for both the thicknesses. We don't vary the stiffness, but we vary the maximum load and the behavior after the maximum load. By varying G2C, we also have a similar variation, but with less magnitude when we vary G1C. By varying G1C and G2C simultaneously, we have the biggest variation because here we are summing the effects of G1C and G2C. By varying the tensile strength of the adhesive, here we have a significant different behavior because now we have very in the stiffness and a smaller deviation peak load. The same occurs for the shear strength, but here the variation in stiffness is greater. And by varying the 2 strengths simultaneously in tension and in shear, and varying all the parameters simultaneously. So we can see that all of the parameters that we input the models are important, and that to have good results, we must actually have these parameters properly characterized, because otherwise we are not going to have a good strength prediction in these joints. And finally, to conclude, I would just like to summarize everything that was said. experimentally, we obtained the alpha parameter of the cohesive loss. In the numerical simulations, we were able to have excellent predictions up to an adhesive thickness of 1 millimeter, but after that we started having slight deviations. The envelopes were only accurately predicted for thicknesses of 0.1 and 0.2, and then we started having slight deviations. And also we checked the influence of the cohesive parameters in the results of the p-delta curve of the SLB test, which tells us that actually all of these parameters must be carried out and defined with accuracy. And this concludes my presentation. Mr. Chairman, thank you so much for the opportunity. And if there is any question from the audience, I'm available and happy to answer any questions. Thank you.